yeah, something different. Maybe a little more down to earth. I don't know. Sometimes I say that, and it's not really. But to me, a little more down to earth. I don't know if you will agree. I want to talk about what we call metric spaces. And we're going to talk about metric spaces for the next few times. This is a very important sort of special type of topological space, you know. I guess the only one that we've had so far was like Hausdorff. That's a nice kind of topological space. Some topological spaces are not Hausdorff, and those I think of as being the really weird ones. Some are Hausdorff spaces. Metric spaces are another category of topological space, which is actually even a bit nicer than being Hausdorff. Like it's a theorem that every metric space is Hausdorff. Metric spaces are a little bit nicer, and they are much more down to earth in the sense that this is a concept that I think ordinary people would come up with on their own. Unlike the concept of a topological space having those, like, you know, finite intersections and unions property, that's pretty far out in my opinion. But the metric spaces is much more down to earth. Anyway, this is a metric space is a set with some metric, which is to say a distance function. So this is just any set in which you can measure the distance between 2 points. This would include Rn in any dimension, but also there are other kinds of sets in which you can talk about the distance between 2 points. That's called a metric space, is a set with a metric. And whenever you have a distance, you can talk about topology. Now, topology you don't require distances to talk about topology, but certainly if you do have like a scenario in which it's possible to measure the distance between things, you can definitely do topology in that setting. So let's talk specifically, what does it mean to be a distance function? There are, like, not any function can be used as a distance function between 2 points. So the metric looks like something like d of x comma y is how we're going to write it. D for distance equals, and it's going to be a real number answer, right? Just because that's what a distance. We have to think about, like, what does it even mean to be a distance? Like, what kinds of things count as a distance function? First of all, it's a function of two variables because you plug two things in and you find the distance from one to the other. It should be a real number. The answer should be a real number. And it should satisfy some properties. Satisfying some properties that make it sort of sensible as a distance. There are certain things that wouldn't even make sense to count as a distance function. Anybody want to suggest some properties that the d function should have in order for it to make sense as a distance? Yeah? It should be positive. Yeah, this is what I was hoping somebody would say. This is the most obvious. Actually, I'm going to write down 3 properties that a metric must satisfy. The first is that the answer you get, this real number here, has to be positive. Now, do you mean positive or 0? I guess, yeah, you should allow, I mean, it is possible that the distance could be 0. If you plugged like the same point twice, distance from x to x ought to be 0. So it should be positive. Or 0, but actually the 0 should, if you ask me, I would say it should only be 0 when the 2 points are the same. Like, you don't want for 2 different points to have distance 0. That wouldn't make much sense. So that's the first property, and let's just write this as a definition. All of what I just said is going to be the first property. So I'm going to say for a set X. Actually, X can be any set. It doesn't have to be a topological space, but we're going to talk about the relationship. A function D so the domain and range are like this. x cross x to R. That is to say, what you plug into D is a pair of points from your set X. And then the answer is a real number. I shouldn't have a comma there. A function D, blah, 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 is a metric when it satisfies these three properties. So the first property is that the answer should always be positive or 0. So that is to say, distance from x to y is greater or equal to 0 for all x and y in X. And furthermore, there should not be any points that are distance 0 apart from each other except for one point with itself. So the way that I'm going to write that is, and if distance x to y equals 0, then x equals y. The only way for 2 points to have distance 0 is if they are actually the same point. All right, this is the first property. It's that the distance between any 2 points has to always be positive or 0. And this thing about if it really is 0, that only happens when x equals y. There's sort of a slogan for this. This is referred to as positive definite. So positive would just mean the values are always greater than 0. Positive definite means it's always more, greater or equal to 0, and it's only 0 when the two things are equal to each other. That's the positive definite property, which I'm often going to write pos def. All right. Anybody have another idea? So I said there were 3 properties. The next one is very simple. The third one is a little complicated. But anyone have another idea about what a distance function should satisfy? The other two are, I would say, less obvious. The first one is what I was hoping everyone would come up with. If I'm thinking about the distance from one point to another, any other ideas? I will give you a moment, and then I will tell you. These are less obvious, but another thing that is important about a distance is that it is symmetric. How about that? That's a hint. Symmetric. Anyone have an idea of what I mean by that? Yeah.
D of x, y equals d of y.
Yeah, right. The distance from x to y should equal the distance from y to x. I would say if you are thinking of a function that doesn't satisfy that property, it wouldn't make sense to use that function as a distance. The distance between 2 points is supposed to be the same if I measure from one to the other versus from the other to the first one. Those are the same distance. All right. If that's not true, then what you can be talking about something, but it's not a distance. Okay, and the last one is a very specific property about distances, which has a name that you're all familiar with. This is the triangle inequality. And that says, well, I'll write it down. The distance from x to y plus the distance from y to z is greater or equal to the distance from x to z. That's called the triangle inequality, and it's a basic fact from geometry. But this is also a required condition in order to be a metric. So why it's called the triangle inequality is it's sort of just inspired by this picture. If my 3 points are like that, x, y, and z, the distances, make a triangle. This one is distance from x to y. This one is distance from y to z. And this one is distance from x to z. And the triangle inequality says that sort of the straight one is shorter than these two added together, less than or equal. All right? This is the triangle inequality. The distance around the two sides is more than the distance across the one. All right? This is also required in order for a function to count as a metric or a distance function. And that's it. So if all 3 of these properties are satisfied, that's called a metric. And now, as usual, in this class, topology on a set is based on quote unquote open sets, even though they don't necessarily look like ordinary open sets. We're going to talk about metric spaces in this way. Usually when I draw pictures, I will imagine that the D represents the ordinary distance in R2 or something like that. But D, so this function D could be the ordinary distance function in R2 or some other thing, right? Where that, everybody knows how to find the distance between 2 points in R2. Or it could be just any other weird thing. As long as it satisfies the 3 properties, it counts as a metric. So I will just say, or any other thing satisfying the 3 properties. And whenever we prove a theorem about metric spaces, the entire proof is just based on those 3 properties. All right, they are like axioms for what counts as a metric. All right, any other thing which satisfies those 3 properties. All right, we're going to talk about a lot of examples. So one example of a metric is what I said, the ordinary distance in R2. It does satisfy those 3 properties. But there are other things that you can use for your metric instead of the ordinary distance. And those other things actually are useful in some situations. In the real world, usually we use the ordinary distance, but oftentimes we want different distance functions. Let me just say a very simple bit of terminology here. If some set X has a metric D, then we say the pair X comma D is a metric space. All right. So just like a topological space is a set which has a topology, a metric space is a set which has a metric. All right. And what we're going to try to talk about, and we're not going to get there today, but today we're mostly just going to do some examples. But the sort of big questions to ask would be, what's the relationship between metric spaces and topological spaces? In particular, is every metric space a topological space? What I mean by that is, if you have a distance, can you somehow use that distance function to create open sets and then turn that whole thing into a topological space? And then the other way around also, is every topological space a metric space? That is to say, if you have one of these distance functions, can you turn that into a definition of no, sorry, that was the first one. Is every metric space a topological space? That means if you have a distance function, can you turn that into a collection of open sets? The other one is the other way around. If you know what the open sets are from some topological space, can you somehow use the open sets or use the neighborhoods to create a distance function? That would be the other way around. Spoiler alert, the answer to these questions, one of them is yes and one of them is no. But we will get there eventually. Before we get into this too much, let's talk about some examples. So examples of metric spaces. We'll start with the simple ones, and then we'll get to some more, a little bit more interesting ones. Metric spaces. First of all, you can make R into a metric space. R is a metric space using the distance function. Anyone want to suggest how we should define the distance in R? This is, what I'm about to write is something you've all seen before. If I just have 2 numbers, x to y, what's the distance from x to y in R? This is not a trick question. Nobody wants to say it. Yeah?
The absolute value of x minus y.
Absolute value of x minus y. Great. Yes, I said it was not a trick question. I actually expected someone to say y minus x without the absolute values, and then I would have said, ha! You're wrong. It was a trick question. You got to put the absolute values, but he put the absolute values to begin with. Yeah, this is the correct way to do the distance between two numbers in the real line, is the absolute value x minus y. All right, is that really a metric? So you need to think this through. Think about the three properties. Is it really a metric? So it's, is it a metric? So we got to think about positive definite. That one is that, you know, you're going to have some homework problem like, here's a thing, show that it is or is not a metric, right? You have to show the three properties or find one of the three properties that doesn't work. Is it positive definite? That is to say, is this thing always positive? Is that true? The answer is yes, it is always greater or equal to 0. And the other part of positive definite said if absolute value, if the distance equals 0, then x equal y. And I think that also is true, right? This is, I just wrote the positive definite conditions using the absolute values, but both of those things are obviously true in my opinion. All right, the absolute value is always greater or equal to 0, and when this thing is 0, that means that x equals y. Okay, that's the positive definite. What about the symmetry? This would say absolute value x minus y is the same as doing it the other way around. Absolute value y minus x. Is that really true? Yes, it is really true. So this is symmetric. And then the last one is the triangle inequality, which I suppose is a little, I mean, when it comes to doing problems like this on the homework or whatever, you will find the triangle inequality is often the one that's a little bit of a pain to check, only because it's just the most complicated one. But this would say the distance x to y plus the distance y to z is greater or equal to the distance x to z. Right? That's the triangle inequality. And is that really true? I will say yes, that's really true. I mean, we use this fact all the time in real analysis when you want to do, you know, like an epsilon over 2 kind of a situation. We use the triangle inequality. Usually in analysis, usually we write it the other way around. That thing is less than or equal to that other stuff. This is also true. It is actually a little bit of a pain to prove this in R1. I don't want to get into the details. This is also true. I mean, I would call this the triangle inequality for real numbers. All right, I don't want to get into it. So R is a metric space using that as the distance. And in my opinion, that's kind of the only sensible distance to use. I mean, that's the distance that we always use, all right? There are other distances you can use in R. I have one stupid example. So that one I would call, if anybody starts talking about distances in R, I assume that they're talking about this. But there are other metric functions in R. I'm going to call this one, so in R, we can use D, I'll call it disk. This is a stupid one. Actually, I have to be a little bit more complicated than that. I'm going to say it's 1 if x is not equal y, and it's 0 if x equal y. All right. This just says all points are distance 1 away from each other, except for one point with itself is distance 0. This is sort of, I said, a stupider example. There's a name for that. I wrote the little disk there. This is called the discrete metric. Why is it called the discrete? You know, in topology, discrete kind of means you are imagining that all the points are sort of far away from each other. Like the neighborhood of each point doesn't contain any other points. That's how the discrete topology works. And this metric works in the same way. Any 2 points are just defined to be distance 1 away from each other. So all the points are far away from each other. All right? Now, you might say this is a stupid way to measure the distance between 2 points, and I would agree with you, but it does satisfy the 3 properties of a metric. So this does count as a metric. Can we just very briefly talk through the 3 properties? There's the positive definite one. That says that distance from x to y is greater or equal to 0. Is that true of this definition? I think it is. The answer is always 1 or 0. So yeah, it is always greater than or equal to 0. And the other part, distance from x to y equals 0 implies x equal y. Is that true? That is also true, because the only way the distance can be 0 is if x equal y. So that's sort of part of the definition. It is positive definite. All right. What about the symmetry? This would say that the distance from x to y equals the distance from y to x. Is that true of this definition? Yes, that is also true of this definition. If x and y are different, then you get 1 both ways. And if the x and y are the same, then you get 0 both ways. But it doesn't matter about the ordering in which you plug them into the function. And then the last one is the triangle inequality. And actually, this one is not so hard to prove in this particular example. So I would say I want to show that the distance from x to y plus the distance from y to z equals the distance from x to z. Not equals, greater or equal, right? Anybody want to say, can you explain, it's not so hard to see, that this inequality is actually true? Let's just imagine that x, y, and z are all different. Then what would you say about these guys here? Yeah?
It's going to be 2 is greater than 1.
Yeah, if x and y are all different, x, y, and z are all different, then it's going to be 2 on the left side and 1 on the right side. So it is greater. And if one of them is equal to the others, then you know technically you'd have to work through a bunch of cases. If some of them are equal, then it's not 2 and 1, and then it's 1 and 0, or 2 and 0 in some cases. Can it be 2 and 0? Yeah, if x and z are equal, but not equal to y, then it would be 2 and 0. But anyway, it's always more on the left than on the right. So can I just say if x not equal y and y not equal z, I mean really if x, y, z are all different, then it says 2 greater or equal to 1, which is true. And if there are some equalities, really, technically, there's a few cases to check, but they're all simple to check. I will say other cases are similar. All right, so the discrete metric is another way of making a metric on R by just defining all the points to be far apart from each other, distance 1. All right. You might wonder, can we do an indiscrete metric? The indiscrete topology, or is also known as the trivial. That's when everything is always there. The only neighborhood is like the whole set, right? That's the trivial topology or the indiscrete topology. Actually, that one is as if all the points are basically like the neighborhood of any point includes every other point. For that one, you would have to sort of define the distance to always be 0. Although that would not be positive definite. If you make the distance equal 0 every time, then this will not be satisfied. So there isn't really a indiscrete metric in that same way. All right, anyway, this is pretty much all we need to say about metrics on R. This is basically the interesting metric on R, and we're not going to talk about other metrics on R. There are others, but they're weird. Okay, let's talk about R2, metrics on R2. So there are actually in R2 a few different interesting metrics that are not stupid. You know, there's the ordinary metric in R2. So this I will call this the standard metric, or sometimes called the Euclidean metric. This is the ordinary way of measuring distance in R2. Our book writes it like this. If I have the distance from 2 points, P and Q, they like to use P's and Q's in R2. I won't argue with that. P and Q, each of them is in R2. So actually, if I were to write this in coordinates, the P I'm going to write as a P1, comma P2, and the Q I'm going to write as a Q1, comma Q2. All right. That's because these are in R2, so I can write their coordinates. And then what is the distance? The standard distance in R2, that's, you know, if I have P1 comma P2 down here and Q1 comma Q2 up here, the distance is that one, and the way you find that distance is typically using something like the Pythagorean theorem. You would draw this triangle. This horizontal distance is Q1 minus P1. Right? This vertical distance is Q2 minus P2, and then you use the Pythagorean theorem to find the hypotenuse distance. Anyway, what you get is this. This is actually, it is the standard Euclidean metric is actually kind of a pain to work with because it has a square root and a bunch of squares in it. So this is, I'm going to write it this way around, P1 minus Q1 squared plus P2 minus Q2 squared. This is the standard Euclidean metric. All right. It's a pain to work with because of the square root sign and all that other business in there. It's a complicated formula. If you didn't know any better, you would look at this and say, how did anyone ever come up with that? It's crazy. There are good reasons to do it in this crazy way, right? It's because of this. Pythagorean theorem is how they would come up with that. All right. By the way, Happy Pi Day. It was during break, so I couldn't celebrate with you. But I hope you had a good one. I should just say, this is a metric. I don't think we need to write out all the details. But everybody knows in R2, when you measure distance in this ordinary way, it is positive definite. Because I'm using a square root, this answer will always be positive. And the only way that this square root can be 0 is if the thing on the inside is 0. And the thing on the inside is the sum of two squares. So the only way that can be 0 is if each of these individual things is 0. And that means P1 equals Q1 and P2 equals Q2. So what I just said out loud is a proof that it's positive definite. It is also symmetric. I'm trying to just talk through the three properties of a metric. It's also symmetric because this is what you do if you do P then Q. It looks like that. If you do Q then P, that has the effect of rearranging the order inside the squares. But since they're inside squares, rearranging the order there doesn't matter. You flip the sign, but you're going to square it anyway, so it doesn't matter. And then it also satisfies the triangle inequality. That is really a pain to show using this definition of the metric, but it's not so hard to do, and I don't want to get into it. Since you've done it, I mean, you probably did that in high school maybe, showed that the triangle inequality is satisfied for the standard Euclidean metric. All right, this is the standard metric in R2. And like I said before, if somebody just is talking to me about distance in R2, I will assume that they're talking about this distance, the standard Euclidean metric in R2. But there are others. I want to talk about two other examples of interesting, not stupid. So I should say, you can also do the discrete metric in R2. Just in R2, say all points are distance 1 apart from each other. That will still satisfy the properties of a metric. But that's a little silly. Here is another example. Two other metrics which are not stupid, but they are interesting and they are different from the Euclidean metric. One is this. Our book writes it as dt, and I will tell you the definition. P1, P2, Q1, Q2. In many ways, this dt is nicer than the standard Euclidean just because it doesn't have a weird square root in the definition. Here's the definition. It is P1 minus Q1 in absolute value plus P2 minus Q2 in absolute value. All right. That's the definition of T. Let's draw a picture and see what does that look like in R2. So in R2, the standard Euclidean metric would be the diagonal distance, but that's not what this is. What is this on the picture? It is more like doing the distances in each coordinate separately. So this first thing, what I see here, P1 minus Q1, that actually is the distance horizontally between these 2 points. That would be this distance here. That is absolute value P1 minus Q1. It's just the distance between their x-coordinates. And then P2 minus Q2 is just the distance between the y-coordinates. So that would be like this one. Absolute value P2 minus Q2. All right. So what I'm getting is the distance from one point to the other is the sum of those two distances, the horizontal direction plus the vertical direction. So this is, if you wanted to think of it in words, this is the distance if you can only move horizontally and vertically, right? If you're for some reason not allowed to go diagonal, then this is the distance that you will experience if you're trying to get from one point to the other. All right? And this is referred to as, so the reason they use this T here, this is called, this has a cute name, the Taxicab metric. Also known as, for people who like alliteration, this is also called the Manhattan metric. This is the distance that you will experience if your movement is confined to a grid. If you're not allowed to go diagonally, then this is the distance. Rather than the Euclidean is kind of like the crow flies distance. This is the moving along the grid's distance. All right? And I'm sure you can imagine there are many situations in which this distance is more important than the crow flies distance, right? Like if you're talking about, navigating car directions, the Euclidean distance between your starting point and ending point is not really all that important. What's more important is the distance along the roads, not just if you were to drive straight through. So the taxicab metric is actually fairly useful in certain types of situations. And also, I like it because the definition here doesn't involve square roots and squares. So just from a practical like algebra point of view, this is often easier to handle if you're trying to prove things about metrics or whatever. All right. Can we try to, I would actually like to go through the three properties for this. So this is a little weird, and it is right if you are a little concerned, is this really going to satisfy all the properties that we want? All right, so let's talk about these. Let's show it's a metric. We must demonstrate the three properties. All right, maybe I'll copy the definition down here. We must demonstrate the three properties. The first is the positive definite property. All right, so you have to show that the distance, this, just to make things easier, let's call the first point P, if I don't want to write the coordinates, P and Q. So in this case, I want to show that, first of all, distance from P to Q is greater than or equal to 0, and also that if the distance really is 0, distance PQ equals 0 implies P equal Q, right? This is what you have to show for the positive definite property. So really for the positive definite, there's really sort of two parts to demonstrate. So let's talk about the first one first. Distance PQ greater than or equal to 0. This hopefully is just obvious by looking at the definition. Is it obvious to you by looking at the definition that this thing over here is always greater or equal to 0? I think it is. Those are each, I have two absolute values being added together. I suppose it is possible for this to equal 0, but it certainly can never be negative. All right, so can I just say this distance P to Q, if I wanted to explain, I would say is absolute value something plus absolute value of something else, and that's always greater than or equal to 0. All right, this is a sum of absolute values. So we do, it's not possible that that could end up being negative. All right. What about the other part? dPQ equals 0 implies P equal Q. All right. So for this one, I'm going to assume distance P to Q equals 0, and then somehow demonstrate that this means that P must equal Q. All right. If I assume distance PQ equals 0, that means this thing equals 0, and we can just sort of do a bunch of simple algebra here. So P1 minus Q1 plus P2 minus Q2 equals 0, right? That's what we assume. Now, What does this mean? I eventually want to conclude that P is the same as Q. If I have two absolute values together, which add up to 0, I think that means each of the two parts individually must be 0, because each of those absolute values has to be positive or 0. So I'll say, so that means P1 minus Q1 in absolute value is 0, or absolute value P2 minus Q2 is 0, right? Because if I have two absolute values, both adding to 0, the only way that can happen is if each one individually is 0. And then what does that mean? P1 minus Q1 equals 0? That means P1 equals Q1, right? That's the only way for two, you think of that as being the distance in R1, right? The only way that you can have absolute value P1 minus Q1 equals 0 is if they're equal. I said or here, I meant and. Sorry about that. I saw some puzzled faces, maybe that's why. And they both have to be 0, right? If it was multiplication, then I would have said or. But since they're adding to be 0 and they're both positive, they both have to be 0. All right, and then the other thing. So P1 equals Q1 and P2 equals Q2. That's the only way that that second thing can be satisfied. So that means that the pair P1 Q1 equals the pair P2 Q2. So P equals Q, which is what we wanted to show in that step. All right. And then finally, the triangle inequality. This is always the one that's a little bit of a pain. So for this one, we want to show that distance P to Q plus distance Q, I'll say R is the next one, is greater or equal to distance from P to R. That's the triangle inequality.
Symmetry.
Oh, I skipped the symmetry. Thank you. Yes, I suppose you can do these in whatever order you want. The triangle inequality, let's do that last because it's the most annoying one. The symmetry is quite easy in this example. That's the one where distance, I want to show that distance from P to Q equals distance from Q to P, right? That's the symmetry property. We should be able to just write down both sides of this and see that they are equal. The left side is P1 minus Q1, absolute value, plus P2 minus Q2, the absolute value. And then the right side is Q1 minus P1, the absolute value, plus Q2 minus P2. And are those two things really the same? The answer is yes, because inside each of those absolute value signs, you can flip the order and it doesn't matter. So I will say these are the same. All right. Thank you for reminding me of the symmetry property. It's easy in this example. Is that because you just didn't want to do the triangle inequality? That sometimes is the case. I've been there. Maybe I am there right now. This one also is not very difficult. We just have to write down everything. So I'm going to begin on the left side. I have distance P to Q plus distance Q to R. All right, this I'm going to say is equal, just writing out the definitions, absolute value P1 minus Q1 plus absolute value P2 minus Q2. That's the distance from P to Q. And then I'm going to write plus the distance from Q to R. That's Q1 minus R1 plus Q2 minus R2. All right? I'm going to try to sort of simplify, and eventually use a greater than or equal and say distance from P to R. All right? Okay, this is just expanding the original thing, the definitions. Anyone have a suggestion here? It's not clear what I should do with all of this business right now. And you're not allowed to just ignore the absolute value signs. I know that's always my my go-to trick, but it makes you fail real analysis, and also the absolute value signs are important. What will help out here is by rearranging the order a little bit. I'm going to change the order around by putting I want to put all the ones together and all the twos together. These are all just added together. So write the two sort of things with ones, P1 minus Q1 plus Q1 minus R1, like so. And then I'll put the other ones together. Also, P2 minus Q2 plus Q2 minus R2. All right? And these things, individually, you can do something with those. Anybody like the looks of those? Yeah?
Do you just combine them so it's P1 minus R1 since the Q1?
Yeah, is that, can you like cancel the Q1s? Is that what you're thinking?
Yeah, I don't know.
I think this is what she's thinking. Canceling the Q1s is not really legal, but you can do something like that. In fact, I am going to write P1 minus R1 here. It's not because I canceled the Q1s though. Like, think about what is the general thing you can do. I'm trying to get a little sidebar over here. If I have something like this, what's the general thing you can do in that situation? The answer is you do the triangle inequality. Like the R1, the triangle inequality from R, right, is that. And so that's actually, don't think of it as canceling the Q's. You just do the triangle inequality. Now, this right here is not an equal sign. It's a greater or equal. So in my argument here, that's greater or equal. This is because of the triangle inequality for real numbers. And then what do I do with the second part? That second part is also greater or equal to, here, P2 minus R2. All right, so that step, I am using the triangle inequality from the real numbers. Which if you want to think impure thoughts, you could say I'm canceling the Q's. You're not really canceling the Q's. You are using the triangle inequality. All right, and anyway, what is that? This is distance P to R, and that's what we wanted to end up with. All right, that's the definition of the distance from P to R. Great. So this is the taxicab metric. It really is a metric. It satisfies all three of the properties. Any thoughts about that? It is, like I said, it is useful in many real-world situations. Actually, in many real-world situations, you don't necessarily want to use horizontal and vertical grids, but certainly there are tons of situations in real life where measuring the direct straight line distance is not always what you are interested in. You are interested in other variations on the straight line distance. All right, I got one more in our remaining 7 minutes. One more other interesting metric on R2. By the way, you can do this taxicab metric in any dimension. You can do it in R3 by going sort of, first you go the x distance plus the y distance plus the z distance. It's a little bit of a pain to write out all the details in that case, but it works exactly the same way. Here's one last metric in R2. It's written with a big M. M is for maximum. Here's the definition of that. If I have P1, P2. Again, these are 2 points in R2. This also takes those absolute values, but instead of adding them together, you just choose the bigger one of them. So the definition here is maximum of absolute value P1 minus Q1, comma, absolute value P2 minus Q2. So this again involves looking at the two distances in each dimension. So you think of this as kind of like the horizontal distance and this as the vertical distance. But instead of adding them together as you would in the taxicab metric, you just take the maximum of them. Whichever one is bigger, that's what you call the distance. So this is called the maximum metric. You choose the bigger one. So in a picture, for example, if I have P here and Q here in R2, now you take the straight line, that's the standard Euclidean. In the taxicab metric, you would choose this distance plus that distance, the horizontal distance plus the vertical distance. In the maximum metric, you just take one of those distances, whichever one is bigger. So on my picture, it would be just this distance, because that's the bigger one. If the horizontal distance were bigger, you would use that one instead, all right? This one is a little bit strange, just the max is a little weird. But this also, we don't have time to do it. And anyway, this is gonna be one of your homework problems. This also satisfies the 3 properties to be a metric. All right. So dm is a metric. This one I have less of a cute understanding of when this would be useful in the real world, but this one does come up sometimes also. The max is a bit of a pain to handle. In my opinion, the taxicab metric is kind of the nicest in terms of the formula. This max is slightly weird. Can we talk? We got 4 minutes left. Can we talk about what if you do this using the minimum? That gives you another metric. Actually, it does not. If you use the minimum here instead, it no longer satisfies the properties of being a metric. Can we just try and talk that through a little bit? If I write d min of PQ equals the minimum of this, P1 minus Q1, comma, P2 minus Q2. This actually is not a metric. Why not? Well, it violates one of the 3 properties. Maybe we can just try and think about the 3 properties. Just because it's easiest for me to think about. Is this one still symmetric? I think actually this one still is symmetric. Just think about if I were to interchange the P with the Q, do that over here, you flip both of these, I think you'll still get the same answer anyway, because those are inside of absolute value. So this one is symmetric. That's the easiest one generally to think through. The triangle inequality, I don't even want to think about that, at least unless I have to. Let's think about the positive definite property. So is it true, positive definite, all right? Is it true that distance P to Q is always greater or equal to 0? Look at this formula here. Is the answer always going to be greater or equal to 0? Show me the thumbs. I see some thumbs. I think the thumb should be up, right? This formula here, it is always going to be a positive number. It's just 2 absolute values, and you take whichever one is smaller. So this one, the answer is yes, this part is true. What about the other part? Distance P to Q equals 0 implies P equals Q. Is that really true? That is to say, if this minimum is equal to 0, does that mean that the 2 points were the same point to begin with? I think this is the part which is not true anymore. Can you think about, actually, it's not so hard, to draw an example of 2 points where when you take that minimum, you get 0, even though they are not the same point. They're 2 different points. If I had something like P is here, where could I draw the Q in such a way that this minimum is 0, even if the P and the Q are not the same? It's the minimum of the horizontal distance and the vertical distance. Yeah?
Just be like the straight line, vertical line up.
Yeah, how about put Q straight up vertical from P, or you could also put it straight horizontal from P. The same would work. In this case, so here, absolute value P1 minus Q1 is 0, right? And so the minimum distance from P to Q would be 0, even though P is not equal to Q. But P is not Q. All right, so that means this d min is not positive definite. And so it is not a metric. And so we shall never mention it again. This is an example of something which maybe sounds okay, but turns out is not valid as a metric. All right, I think that'll do it. So next time we're going to talk about the connection between metric spaces and topological spaces. They are closely related, although not exactly the same. See you then.